This is now 7.1b, where we are going to talk about the domain of each of the functions. What you need to remember is that you cannot have 0 in the denominator. Because anytime you have 0 in the denominator, it ends up becoming undefined. So domain, again, is wanting to know your x values. And this is a review from last unit. We've done this already. So the only x values that we have to worry about right now are my denominator values. Whatever would make the denominator 0 is not going to work and cannot be part of our domain. So you set your denominator equal to 0, and we find that the only value that the denominator or x value cannot be is 2. So your answer for your domain is all reals except x cannot equal 2. And that is your answer. On example 2, same thing. You can just set your denominator equal to 0. So if we go x squared plus 4 equals 0, and then if I subtract 4 to both sides, and I have x squared equals negative 4, and if I take the square root, can I take a square root of a negative 4 and get a real number? No, I can't. This will end up becoming an imaginary number. So what this tells us is there aren't any numbers that x can equal that will end up giving you 0 in the denominator. So the answer for this one is all reals. If you get a no solution here, then that means there's no values that you need to exclude. Okay, so on this one we had to exclude 2 because 2 would make our denominator 0. On 1, this doesn't work. Therefore, my answer is just all reals. There's nothing that I can put in for x that will make 0 in the denominator. Okay, example 3. Again, we're going to go ahead and take our denominator and set it equal to 0. X cubed minus 25x equals 0. Hopefully you notice that you should take out the GCF first, which in this case is x. So I take out an x and I'm left with x squared minus 25. Hopefully you notice that 25 is actually a square. So I really have x squared minus 5 squared. And whenever we have a difference of squares, we can factor it. And we just pull apart our squares here in the front, pull apart the squares in the back, and you get 1 minus and 1 plus. And this equals 0. Once you have that, you need to set each of your factors equal to 0. So we have x equals 0, x minus 5 equals 0, and x plus 5 equals 0. And when we solve those, this is already done. Here I add 5, and we get x equals 5. And here I subtract 5, and we get x equals negative 5. So this answer is going to be all reals except x cannot equal 0, 5, or negative 5, because all of those would give you a 0 in the denominator, which would make it undefined. Okay, moving on to example 4. This asks you, when is this statement true? The first thing you should do is simplify it. See if by reducing this it actually equals 5. So if we do this and simplify here, I can take out a GCF in my numerator, so I get 5 and x plus 1 over x plus 1. My x plus 1s can cancel, so I do get 5 equals 5. So that does make a true statement. But what you need to remember is that we cannot get a 0 in the denominator. So once you know that it's true, you know it's probably all reals, except when you would get 0 in the denominator. So if we take x plus 1 and we set it equal to 0 and subtract 1, we get x equals negative 1. So my answer would be all reals except x cannot equal negative 1. And if you go and look at your answers, it is B. Always except when x equals negative 1. Okay, so let's go to number 5. So again, I'm going to take this and see what ends up happening. If I factor out a 3 on the top, I have x minus 2 over 3, and these reduce. So I do end up getting x minus 2 equals x minus 2. So that works. So it's probably going to be all reals, except what number could make the denominator 0? Well, since the denominator is a 3, there aren't any values for x that could change that 3 to a 0. That 3 is there as a 3. You need a variable in the denominator to change that. So this one is just all reals. Therefore, if you look at your answers, it's going to be for all values of x. And that is the end of our 7.1b note.